Video number 4, we're going to explore this concept called the law of sines. And in the next video, we will explore the law of cosines. And you might wonder, well, if there's a law of sines and law of cosines, is there a law of tangents? And there are. There is a law of tangents that works, but we're not going to explore it. We can do everything really with law of sines and law of cosines. So, is there a law of tangents? Yes, but we will not cover it. Now, the law of sines. Are we going to use it right now? No, because I want you to see where the law of sines comes from. So we're going to look at this problem like we would if it was just a normal problem. So let's say I've got a triangle. It's not a right triangle, but I know two angles in this triangle, which means I could figure out the third angle up top, but it's not really going to be necessary. And if I know that the left side is 12, and I want to figure out the length of the right side, okay? I don't want to know what the area of the triangle is. I just want to know what is the length of that right side over here. So, man, if this isn't a right triangle, well, how can we do that? Because we talked about we can only really use trig in right triangles. Well, we might consider making some right triangles, right? We could drop down a height. Again, we're not going to find area, but hey, dropping down a height means we're going to have some perpendicular action going on down here. And now, hey, look, I've created two right triangles. So if I wanted to try to work over here in this right triangle, because that's where x is, right? I'm going to use a 72-degree angle, and I want to know what the hypotenuse is, but I don't know what the opposite side is, and I don't know what the adjacent side is. So I can't really use trig yet, right? But which of these two sides could I maybe figure out in this other right triangle? Well, these two right triangles share the piece I just drew in, the height, right? So let's call it h. So if I came over here to the left side of the triangle, and I said, hey, what if I use the 61-degree angle, and I wanted to know the opposite side, which is the height, and hey, I know the hypotenuse is 12, I could use some trig over here on the left side. I could use sine with 61, and it would be equal to the opposite over hypotenuse, and I'd have to multiply both sides by 12, so that h would be 12 times the sine of 61. Now, what does that come out to be exactly? Well, let's see. 12 times sine 61. 12 times sine 61. Calculator, it is really 12 and a half, or not 12 and a half, 10 and a half, sorry, 10.5. Even if I wanted to round it to 2 decimal places, it would still have to be 10.5. So this is 10.5. Now I could finally come back over here to my right side of this right triangle, and now I could use some trig, because now I know the opposite side's 10 and a half, and so using the 72, which trig ratio would I use? Oh, well, I'd still use sine. And you might start going, oh, hey, look, he used sine once, he used sine twice, and this video is about the law of sines. There might be a connection going on here. So the sine of 72 is equal to the opposite, which is h, which we now know is 10.5, divided by the hypotenuse, which is x. This would be a flip-flop. So x would be equal to 10.5 divided by the sine of 72. And so now if I were to type that into my calculator, 10.5 divided by the sine of 72, I would have figured out that x is 11.04 if I wanted to do 2 decimal places, let's say. So I'd have x. Sweet. So what? I didn't have to use this new thing called the law of sines to figure out what x is. I figured it out. We used sine twice, right? We had to use trig twice, big deal. Well, what if I told you there's a shorter way of doing this, using the law of sines? So you go, all right, I'll nibble. Teach me a shortcut. Well, before we can get to the shortcut, we need to talk about a couple things here. Number one, this is typically how angles and sides of a triangle are typically set up. So let's say I have angles A, B, and C. I would put the side, if I were to name sides A, B, and C, like in the Pythagorean theorem, I would have to put A right here, and I'd have to put B right here, and I'd have to put C right here if I already named my angles A, B, and C. And so the positioning you need to notice here is that angle A and side A are on opposite sides of the triangle. Notice with B, angle B and side B, they're on opposite sides of the triangle. Likewise with side C and angle C, they're on opposite sides of the triangle. So if you were to name a triangle ABC, or here, let's go even different. Let's say DEF. So side or angles DEF, where would sides DEF be? Well, opposite angle D, this would be side D. Opposite angle E, this would be side E. And side F would be opposite angle F. Notice that with angles, I'm using capital letters. For sides, I'm using lowercase, kind of italicized or cursive-y looking letters. So you'll notice that. We'll have to do that to set up some problems. Now, let's go back to the problem we just did. And let's see if we can create the law of sines out of this, aka our shortcut. So initially we used the sine of 61, right? We started over here. We said we want to know the opposite. We knew the hypotenuse. And then we had to go use the sine of 72. So we had to use our 10.5 that we figured out with x, and we solve for x. Okay? Let's see how these two things can really merge into one thing. So if I put angles A, B, and C, and does it matter if this was really angle A or if this is angle A? No, it doesn't matter. So I just called this angle A, angle B, up top angle C, which means opposite angle A, the x was really side A. The 12 was really opposite angle B, so it's side B. And the whole bottom base here is opposite angle C, so this was side C. And again, it really doesn't matter which angles I called initially A, B, and C. I could switch them around, and then yes, that would switch around sides A and B, A, B, and C to their corresponding angles. Okay, so here's what I want to do. Instead of using these numbers, right, because we're not always going to have a 61 and a 72 degree angle, we might have different angles for different triangles. So let's get rid of the 61. Which angle was really the 61 degree angle? The 61, well, that was angle A. Okay, so instead of saying sine of 61, I want to say that was really the sine of angle A. H. Now, H really isn't any of the sides, but we need to use it. It's our connecting link between these two problems, because you'll notice, hey, they both have H's. There's the bridge. Oh, too far. Now, the 12 in this problem, what did the 12 represent? Oh, come on. Come on, come on. The 12 represented which side? Well, the 12 represented side B. So I'm going to put a B in its place. Because again, are we always going to have a 12 in a triangle problem? No. But I can always call it a variable to represent whatever number it may be. The 72 down here. Well, let's not think of it as 72, but let's think of it as a variable. 72 was angle B. Okay? And the x that we were figuring out was really side A. All right? So, geez, I did it again. Okay, so no more x. Let's think of it as side A. Okay. Now, the thing you're going to start to notice is, hey, look, I've got A's and B's here, and I got A's and B's here, and that's something to the law of sines. Now, what I want to do is I want to solve both of these for H. So if I want to solve for H, well, up here I'd have to multiply both sides by B. So H would equal B times the sine of A. And down here I'd multiply both sides by A, side A. And so H would equal A times sine B. Okay, now what? Well, if I know what H is equal to, and they look like two different things, right? But really, if these two things equal the same thing, H, then what needs to be true about these two values if they both equal the same thing? Well, they must be equal to each other, right? So the B times sine A, here, let's put it up here, get rid of you. Or here, think of it this way. Think of substitution, right? Instead of writing this H here, what else is H equal to? Boom, A times sine B. That's another way of thinking about it. Instead of just going, oh, well, if these two things both equal the same thing, they must be equal to each other. You can kind of think of it as substitution. So A, side A times the sine of angle B needs to be equal to side B times the sine of angle A. Now, all I'm going to do here is move some stuff around. Now, multiplication, multiplication, so if we need to move things around, we're going to have to divide, right? I'm going to divide both sides by side A, all right? And at the same time, I'm going to divide both sides by side B, so that that's gone over there, that's gone over there, and so if I erase those so they're no longer there, look what I've got here. You might go, why did you do that? Well, look, I've got angle B with side B on the same side of the equation, and I have angle A with side A on the same side of the equation. So here is really the law of sines. It's the sine of an angle divided by its opposite side, right? Because side B was opposite angle B, is equal to the sine of a different angle divided by its opposite side, right? Because side A is opposite angle A. So this is kind of our shortcut that we can use. If we understand this is the law of sines, we could say, hey, sine of B, well, what was B? B was 72. We can plug 72 in right there. Side B, that was 12. Angle A, that was 61. And A was X. So this is just some number. This is just some number. So if I've got a fraction equals a fraction, you got to think back in the day to Algebra 1. How did we solve these things? Oh, well, we would cross multiply. And so you can cross multiply and solve for X. Okay? There are some, we could have kind of written the law of sines a little differently here so that we always get like an X equals, but the X may not always be in this bottom right corner. The X could be an angle. The X could be this side over here. It could switch up. All right, so when are we going to use the law of sines? We're going to use the law of sines when we want to figure out missing sides and angles, but we need to know two sides and an angle, or one side with two angles. So essentially, we need to know three pieces of information about the triangle, but the three pieces of information can't all be angle information, and it can't all be side information. So we got to have a mixture of sides and angles, 2 and 1, and it doesn't matter if the 2 are the sides or 2 are the angles. Now, here's the absolute best part in the world about the law of sines. Earlier we said we can only do sine, cosine, tangent, trig in right triangles, but the law of sines does not apply to just right triangles. Law of sines is going to work for any triangle, right triangles or not. So here's what's called the extended law of sines. We can really only do two pieces at a time. Okay, and here's what we originally had. We talked about A's with B's. But what if we were talking about B's with C's? Well, then we would just do this. What if we were talking about A's with C's? Well, then we would just kind of ignore the B part. And we'd have this is equal to this part. Okay? So the law of sines works with the same letters, but the angle and the sides are the opposite of each other. The angle and side are opposite of each other. The angle and side are opposite of each other. So you see three things, but we can only use two things at a time. Okay? So why couldn't I use C in this problem? Well, C was the thing that got split up, right? Angle C got split up between two angles, and side C down here got split up between two pieces. So that's the letter I'm not going to use with the law of sines, okay? That's kind of your clue to which one you're not going to use. Now, in addition to the law of sines looking like this, I could write it like this instead. And what really changed? Well, all I did was I flipped each of the fractions. And if you flip one, you got to flip them all. Okay? So this, if you remember flipping fractions, was really just called the reciprocal. Now, which version do I use? I think I really use this top version, but you could use the bottom. But again, as long as the letters match up top and bottom, it truly doesn't matter if sine's on top or sine's on bottom. But if you say sine's on top, it's always got to be on top. If sine's on bottom, it's always got to be on bottom. You got to be consistent. Okay? So for example, you can't say the sine of angle A divided by side A is equal to side B over sine of angle B. Well, you said sine of A, or you said sine was going to be in the top, and over here you said sine was in the bottom. That doesn't work. That's no longer the law of sines. You've screwed it up. So let's try an example out here. And I've even got a word problem. Oh my gosh, what are you doing? So I've got triangle ABC. So how about we draw a picture of triangle ABC? What kind of triangle should you draw? Who cares? Just draw a triangle. This thing just won't be drawn to scale. So I need to call it ABC. So here's A. Let's call this B. Let's call this C. Could I have made A, B, and C in different spots? Yes. Does it matter? No. Angle A is 22 degrees. There's angle A. Angle B is 31 degrees. Boom. Now notice this says C. It's a lowercase c, so this means side C, which is opposite angle C. So this is 58. And I want to figure out what is A, which is side A, which is opposite angle A. So there is what I want to figure out. Okay? So here's the thing. I know I need to use A, which means I'm going to have to use angle A with it, with the law of sines. So I can already start setting this thing up. I'm going to use the sine of 22 over A. I just need to figure out, am I going to use B's or C's with the A's that I've already used here? Well, if we look, we got to look. Can I use B's, let's say? Well, I know angle B is 31, but what's the length of side B down here? I don't know what it is. So guess what? We're not going to use B's in this problem. So let's look at C's. You might go, hey, I know side C, but look, angle C, I don't know what it is. But we could figure out angle C because we know two of the angles in this triangle. It's 22 and 31. So if we took 180 minus 22 minus 31, we're really subtracting away what? 53? So angle C must be 137 degrees. So angle C, 137. So I know angle C and side C. So I'm going to have, since I did sine in the numerator, I got to do sine numerator over here. 137 divided by side C, which is 58. So now I have a proportion. I have a ratio equals a ratio. How do I solve this thing? Again, earlier I said, hey, we're going to do some cross multiplying, and you're going to do that a lot with the law of sines and cosines. So let's move all this up here, and let's do some cross multiplying. So A gets multiplied with the sine of 137, and the 58 gets multiplied by the sine of 22. Now, I could figure out, well, what is that? I'm just going to leave it the way it is, as 58 times sine of 22, and I'll worry about it later. If I want to solve for A, it's being multiplied with the sine of 137, so I need to divide the sine of 137. Remember, that's just some decimal number. So now here's where we can use the calculator. A is going to be equal to whatever this is in the calculator. So if I'm typing this into the calculator, this is where we're going to have to watch out and make sure we use appropriate parentheses. So if I'm typing this in the calculator, I'm going to type 58 times sine 22 end parenthesis. Make sure you end the parenthesis after that 22. Otherwise, this sine of 137 it's really going to be like the sine of 22 divided by the sine of 1. It's like we're taking the sine of a sine angle, and that's really not what we're wanting the calculator to do. So in that parenthesis, then say divided by sine of 137, and just as common practice, end the parenthesis after the 137. And so I get that A is approximately 31.86 if I were to go 2 decimal places. And there's the length of side A. And we are done. Are we? Are we? We'll have to talk about it. I think we are. Yeah, we're done. We're good. All right. Example 3, I want you guys to try on your own. Okay, and I drew a picture for you just so you have it there. What you might consider doing is labeling angles A, B, and C. So maybe I call the 82 angle A. I'll call this angle up here B, this angle over here C. So if this is angle A, that means 14 is side A. If this is angle C, then the 10 is side C. And so my blank one over here has got to be side B. So in this problem, you're not just figuring out one thing, you're figuring out all missing side and angle measurements. So you have 3 things to figure out here, which means you could use the law of sines multiple times. So you're going to need to figure out what is angle B, what is angle C, and what is side B. And I'll give you a little hint here about where you need to start. Look at what you absolutely know in this problem. Which combination you know both values of. You know side A and angle A. So you know that you're going to be using the sine of 82 over 14. And so now you need to set up a problem using B's and maybe a problem using C's. And you might go, hey, I don't know anything about the B's, so maybe you can't start there. Maybe you should start with angle C. And if you're solving for an angle, remember how you're going to have to get rid of the sine, maybe second sine. So we will go over this one together tomorrow in class. And that's all for video number 4, Law of Sines.